All right, so one very important thing about polar representations of complex numbers is that it makes rotations so much easier. And that would make sense, right? Why? Because polar forms are just based around angles. So it would make sense that if you want to do like a 45 degree or 60 degree or however many degree rotation, it's easier using polar coordinates because, they're based around angles. So in this video, I'm just gonna show like how and why that is. So first, just to show, oops, let's say we have um, some coordinate on the unit circle. Um, oh dear, this is gonna be the point on our beautiful unit circle because I am clearly very good at drawing circles. And let's say this is at the angle pi over 6. So this is gonna be skirt 3 over 2, and then 1/2, except since this is a complex number and it's on the arcant plane, and this axis is real, and this axis is imaginary, this number is actually going to be square root 3 over 2 plus 1/2 I over 2. And we can also represent it as cis pi over 6. Well, if we were to rotate it just 30 degrees, all we would have to do is just bloop. We are adding 30 degrees, or in other words, pi over 6 more, and now it is right here. It's at 1/2 square root 3 over 2. So, or if we wanted to add maybe 45 degrees, it would be right here, right? No, it wouldn't. It would be right here at 75 degrees, somewhere over there. And so we can do that for any number of angles, like if we wanted to add, let's say, why do it take so long? Like we wanted to add 2 pi over 3 degrees, we could easily do that. That would be somewhere over here. And so it would be pretty easy to find our new angle. All we have to do is just our new number, all we have to do is just add a certain amount to that angle. And so that's why when you want to rotate a number, it's so much easier to do it in polar form, because remember, all you're doing is adding whatever amount you're rotating by to that angle. And so this is why we can think of this a few different ways. So let's say this number, which you said already, this is equal to e pi over 6i, right? According to the exponential forms of complex numbers. And so if you want to rotate this by, let's stick to 2 pi over 3 degrees. You want to rotate this by 2 pi over 6 degrees? Well, then to this angle, you're just adding 2 pi over 6, right? And so we're just adding, when we rotate this, by, sorry, did I just say 2 pi over 6 degrees? Anyways, when we rotate this by, let's say 2 pi over 3 radians. So that would be, can I do math? Really not. That would be 120 degrees. So 2 pi over 3 or 120 degrees. Okay, so when we do that, what we're doing is we're adding that amount to the angle. So this becomes cis of pi over 6 plus 2 pi over 3. Or we can think of this as e raised to the pi over 6 I plus 2 pi over 3i. And so what's another way that we can get of e of pi over 6i plus 2 pi over 3i? Well, this is the same thing as saying e raised to the pi over 6i times e raised to the 2 pi over 3i, right? And so when do we get this? Well, this is the same thing as taking our original number, which was e to the pi over 6i, right? That was our original number, square root 3 over 2 plus 1 over 2i, and multiplying it by cis of 2 pi over 3, right? Because that's all e of 2 pi over 3i is. And so for that reason, we can say cis, this is kind of a function used for rotation, because when we multiply a number by cis of whatever, what we're really doing is we're rotating it by that many angles around the plane. Now, if cis has some radius in front of it, so it will say, for example, is 4 cis 2 pi over 3i, then not only are we rotating it by 2 pi over 3, but we are also stretching it so that it's 4 times, the radius is 4 times as much. But that is why rotations are so much easier, in my opinion, on a complex plane, because all you're doing is multiplying it by cis or adding a certain amount to the angle. But don't for a second think that this has to be limited to just complex numbers, because I know the rules say like cis pi over 6, that is equal to cosine pi over 6 plus I sine pi over 6. So it has to be a number in the form a plus bi. But let's imagine for a minute that this were not the Argand plane, and this were instead the x and the y axis, and this coordinate was not square root 3 over 2 plus 1 half I, but it was instead square root 3 over 2, 1 half. Let's imagine it were that. And then, let's say we wanted to rotate this coordinate by 120 degrees. Well, what we can do is we can just pretend that this very real coordinate is in the complex plane, and say it's this, and then we rotate it by 120 degrees, okay? So we get that the new value is cis pi over 6 plus 4 pi over 6, so 5 pi over 6. And so this means that our new coordinate, cis, this is equal to cosine of 5 pi over 6, so that is a negative square root 3 over 2 plus 1 half I. So this is the new coordinate. But, this, we can just, this is, we converted it to something imaginary and it has an I in it. But, 5 pi over 6 is right here. But, we converted it to something imaginary, and all this is telling us is what our x is and what our y is. So in the real plane, in the Cartesian coordinate system, this coordinate would be square root 3 over 2, 1 half when we rotated it. And so, yes, like we didn't need to do this in this specific scenario because we could just have, this was on a unit circle, we could have just added this certain amount. But my point is, when you have numbers that aren't as nice and they're real, you can still convert them to polars and imaginary polars, use cis to rotate them, and then convert them back to real, and your cosine and sine just becomes your x and your y, respectively. Anyways, so yeah, that's how you rotate complex numbers in polar form.